we are going to explore how to build an efficient key value storage system with limited capacity. This concept is at the heart of LRU cache, least recently used designs. But more importantly, we are going to generalize the data structure techniques behind it. We'll learn how to combine hash maps and linked lists to get both speed and order tracking. We are storing key value pairs very similar to what a hash map does. The twist here is we are limited by a fixed capacity. If we go over the capacity, we can't randomly remove keys. We must remove the least recently used key. And once we remove the least recently used, we need to remember which one comes next in line. So we must track usage order. Naturally, we start by thinking, let's use a hash map. A hash map allows constant time lookup, insert, and update. But there's a flaw, it doesn't remember the order in which the keys were used. If we need to remove the least recently used key, a regular hash map has no idea which key that is. This is where things start to get tricky. We need a way to track the order of how keys are used. A queue is a natural fit. Think of it as a line. Front of the queue is least recently used and back is the most recently used. When a key is used, move it to the back. When we insert a new key, add it to the back. When we hit capacity, remove the one in the front. Seems perfect in theory, but let's explore how to implement it. What if we try to use a Python list or array to implement this queue? To move a key to the back, we have to find it in the list and remove it. But removing elements from the middle of a list takes O of n time. As usage grows, this becomes inefficient. So we need something better, something that gives us O of 1 time for these operations. So we can define our needs now. We have to track the order of the usage and we need the access, insert, update and remove keys in constant time. So our solution is to combine two structures, a hash map to allow fast key access, a doubly linked list to track order and allow fast insertions and removals. A doubly linked list allows fast insertions and deletions anywhere in the list. Example, let's say we have nodes A to B to C to D bidirectional, and if we want to remove C, we can simply update B and D's pointers. This happens in O of 1 time. This is exactly what we need for our move to back operation when a key is used. You might ask, why not a simpler singly list? In a singly list, to remove C, we need to find B, the previous node, but we can't go backward. We have to traverse from the head. This takes off n time, which is not good. In a doubly linked list, every node has a pointer to both the previous and next nodes. So we can directly jump to the previous node and make changes, which is off one again. So here's where the magic happens. In our hash map, we store key um, and node reference. And now, when we want to update or fetch a key, look it up in the hash map of one, get the node, remove it from its current spot of one again, and move it to the back of one, all done in constant time. Let's see how each operations work in OAuth1. Get key, look up in hash map and move to back. Put key value, insert or update and move to back. Evict, remove node at front, least recently used. So the doubly linked list gives us fast ordering, and the hash map gives us fast key access. Our linked list nodes are slightly richer. They store both the key and value. Why store the key in the node? Because when we remove a node from the list, we also need to delete the corresponding key from the hash map. Each node has key, value, prev, nest. This structure is the glue between the hash map and the linked list. Now let's talk about edge cases. What happens when our linked list is empty? Head and tail or null special cases to handle. And what if there's only one node? We'll keep writing if statements all over the place. The fix is to use sentinel nodes, which are just dummy nodes for head and tail. Head.nest is the real first node and tail.prev is the real last node. This approach avoids nulls and makes logic uniform for all cases. This design pattern is powerful beyond just LRU caches. Anytime you need fast access to items by key, tracking usage or insertion order, fast removal of oldest or least used items, and we are combining hash map with a doubly linked list. So we'll often see this in the system design, databases, caching. This pattern is everywhere. Operating systems uses LRU for memory management, web browsers cache recently visited pages, and databases cache queries or pages. We'll be learning not just a technique but a universal tool in real world engineering. Let's wrap up the code takeaways. We use a hash map for a fast lookup. We use doubly linked list for maintaining the order. We use dummy nodes to simplify logic. And we keep node references in the hash map, not just values. This enables all our operations to run in O of one time with clean and efficient logic.